So today is our 39th day. So we have started the chapter that is organic compound containing oxygen. We have completed alcohol, phenol and ether. Then we have moved to the preparation of aldehyde and ketones and aldehyde and ketone. So today we will be discussing about some of the reactions. Okay. So we already know that this is the syllabus that is issued by JEE NTA for the upcoming JEE exam, and we are going to say this one. Okay, so this is the thing that we are covering today. That is nature of carbonyl compound, nucleophilic, all of the nucleophilic additions that we have, and important additions. Then we will see some special reactions like Grignard one and the Wolff-Clemenson one. At last, we will see that alpha hydrogen aldol reaction means the acidity means the reaction that happens due to alpha hydrogen and the reaction that happens due to the absence of alpha hydrogen. At last, we will be covering some of the distinguishing tests that are used to distinguish two compounds in laboratory. So it includes mainly Tolvin's test, filling test, and the haloform test. So that is all about today's lecture. So let us start our today's lecture. So before that, let us see all the topics in a more detailed manner. So first one is the chemical reaction. So basically we are seeing nucleophilic addition and all reactions. So we will see which are the reactions that are possible with this carbonyl compound. Okay, the first one, nucleophilic addition. Then we will see some examples. Then we will see Grignard reagent, which is also a nucleophilic addition. Moving on to oxidation, which is used as a distinguishing test. Again, we have another oxidation, that is haloform reaction. Then we have the reaction due to the alpha hydrogen, and the absence of alpha hydrogen gives us Cannizzaro reaction. Okay. Then we have the reduction. Okay, and at last we have the oxidation. So this was the main detailed chapter topics of today's lecture. So we know I have discussed this also, told you also earlier that average of one question come from oxygen compound containing oxygen, and it is worth of 4 marks. So let us see what are all the reactions that are possible with this carbonyl compound. So the first one is nucleophilic addition reaction. So in this reaction, basically an electrophile attacks. Then in the reduction, then we have the oxidation, then we have the reaction due to alpha hydrogen and other reactions. So let me write it once more. So in this reaction, the electrophile attacks. So we will see this reaction in more detail. So this is the mechanism of nucleophilic addition. So you know very well that this carbonyl center, it is sp2 hybridized. So it is trigonal planar. Like this. And this carbon is less electronegative than oxygen. So we will have a delta positive charge on carbon and delta negative charge on oxygen. We have seen earlier that yes, it is a polar bond and positive charge rests on this carbon because of the resonance structure that looks like this. This is the resonance structure of the carbonyl. So due to this structure, it contributes toward the dipole movement or the creation of dipole on this carbonyl bond. Now what will happen? So we have a nucleophile here. So nucleophile can have a partial negative charge or a full-on negative charge. So we are taking the full-on negative charge. Now this negative charge will attack on this partial positive carbonyl center here. Okay. So it will attack here. Now one of the pi bond, so we have one pi bond and one sigma bond. So one pi bond will move on oxygen. So and it will create a tetrahedral intermediate. So this is important here. So we have two groups A and B earlier. Now since the nucleophile is the third group that is attacking on this, say carbon, so we will have this kind of tetrahedral intermediate. Now due to the movement of pi electron on this oxygen, we have a negative charge on oxygen. Okay. Now in the next step, suppose we are doing it in the presence of H plus, that is acidic condition. So this O negative charge is satisfied by this H plus, and we get the addition product which will look like this. Now moving on to reactivity. So this is the reactivity order. So these are the various carbonyl compounds we have. So it also includes the carboxylic acid and its derivative and aldehyde and all of those carbonyl compounds. So the most reactive one here is the acid halide. So we have this X which is for chlorine and bromine. So this thing is present here, chlorine and bromine. So it is the most reactive one. Then we have the aldehyde and ketone. So aldehyde and ketone are the second. And if you consider specifically, then aldehyde is more reactive. Aldehyde is more reactive. So what is the reason for this? So if you see an ketone group, suppose this is the ketone group, and if you compare it with the aldehyde group, so you can see very well that during the nucleophilic attack, which is the slow process or the RDS, you can say, rate determining step. So in this step, what happens? Nucleophile attack. So the you can say feasibility of the attack of the nucleophile will decide whether the reaction will go slow or fast. Now the feasibility of the reaction or the attack will depend upon the steric hindrance. So there is no such kind of intermediate formation. So it is a kind of SN1 attack, you can say. SN2 attack, you can say. Now since the rate of reaction depends wholly upon this nucleophile and plus upon this this substrate, so you can see that if the nucleophile is same for both of this, so if you have the same nucleophile, then it will depend on the substrate, whole of the substrate, that whether the reaction will take place fastly or not. Now two reasons are there due to which ketones are less reactive. First of all, we have the steric hindrance due to R and R dash. So we know very well that H atom is absolutely smaller than this alkyl group, whatever the size of the alkyl group. So smallest it can be of CH3. Still it has 3 hydrogen and 1 carbon, but this is only 1 hydrogen. So due to first reason is the steric hindrance. And the second reason that we are having here is that, so since we are having an attack of negative on a positive, so it is a kind of electrostatic interaction. So since these two R groups are donating electron density through I effect, so you know this thing. So plus I effect, since R group shows the plus I effect, they will reduce the positive charge on the carbon. The delta positive charge on the carbon will be reduced due to this plus I effect of this both of the alkyl group. While in the aldehyde we have only one alkyl group here. So this will reduce the positive charge, and hence the attack of the negative charge will become less feasible in case of ketone. So second is to plus I effect of both alkyl group. So these are the two reasons due to which aldehyde is more reactive than ketone. Then third we have the thioester. So thioester has a lone pair, so it will resonate, and you can say it will reduce the nucleophilicity of this thioester. Then we have the ester. So since sulfur is of a greater atomic number, or you can say a greater size, so they are overlapping with carbon, which will not be good as the oxygen can do with the carbon, because they are in the same period. Then we have the nitrogen. So since nitrogen is less electronegative than this oxygen, so it will be donating its electron more likely. At last we have this carboxylate ion. Now carboxylate ion is the least reactive one here. Okay, so because oxygen is donating this lone pair, or which is free, it is having a negative charge almost, so it is carrying a unit negative charge, so it will resonate very efficiently. So it is the least reactive one. So this is the order of nucleophilic attack on this carbonyl center. So if you want to place this, say carboxylic acid, it will be here between your ester and your amide group. Now next, let us see some examples of nucleophilic addition. So these are very important examples. So first is the attack of this cyanide group. So we know HCN, so we are doing it in the basic condition. So what will OH minus does? It will abstract this hydrogen from this HCN and we will get a CN minus, which is a nucleophile here, which is carrying a negative charge. Now this CN minus will accurately attack to this carbon and it will create a tetrahedral intermediate. Now again, we take this H plus and substitute it on this oxygen and we get this cyanohydrine. So this is the final product of this attack of this hydrogen cyanide. Now let me make one point clear here is that this reaction is not that much feasible and it reverts back to this carbonyl. So this is not stable one, but of course it is there in the reaction mixture. So if you put some further reagents, it can react further to give your final product, but it is not that much stable. Of course, no, and the case goes for all of this. So if you see, you can see that okay, ketone group is most stable one because it is having a double bond here. So all of this nucleophilic addition are reversible in nature and they can revert back to your ketone at any time unless and until you put a barrier, or you can say you can put a reagent that stops this backward reaction. So second is the addition of sodium hydrogen. So what we are taking? We are taking NaHCO3. Now what will happen? One of the oxygen, so HCO3, if you look like this, it will look like this. Okay, so it will look like this. Now what will happen is that this will resonate like this. Okay, and then it will attack on this thing. So what we will get? We'll get something like this. O S double bond O OH, which is having a positive charge. Okay, so this will look like this. Now what will happen is that since we are having a negative charge on this oxygen, so it will be stabilized by this Na. So this is the overall structure that we have. Okay. Now further we will have an interproton transfer, that this hydrogen will be transferred to this oxygen and this Na will go here. So there will be an interproton transfer here. So we will get this thing. Okay, so this hydrogen get transferred here and this sodium goes here. Then we have the addition of alcohol. So what will happen? So in alcohol, ROH will attack this thing RCHO and we will get similarly this intermediate here, which will look like a ether at a point. Now at the addition of H plus, you can see that one more OH is substituted by this ROH and we get this acetal here. Okay, so this is acetal. We can use ketone also in this place. So if we use ketone here instead of this, say aldehyde, then we will get this kind of product and it is called as ketal. Okay, so it is called acetal because we are having a aldehyde, and if we are having a ketone, we will call this ketal, and the intermediate will be hemiketal. Now next we have a addition of ammonia and its derivative. So we are taking a derivative of ammonia, or you can take it ammonia also. So it can be this Z can be alkyl, aryl, OH, NH2, C6, H5, NHCO2 or H also. So it can be anything. So upon this addition, we will get the similar product one of the H will be transferred on this oxygen, and we will get this intermediate. And at last there is an elimination reaction. Sorry, because one more hydrogen is transferred to this oxygen, and we get a imine. So this is the overall reaction of this, say, or you can say addition of this ammonia. So these are very four important, you can say, reactions. So you should be keeping this in mind. Next, let us see one more nucleophilic addition, which is with Grignard reagent. So what we are seeing is it at the mechanism, because we have seen the Grignard reagent earlier also. So I am not giving you the Grignard reaction of whole. So we have seen that thing in the, say, our hydrocarbon chapter. So I am just giving you the mechanism, because this mechanism was not introduced at that time. So suppose we are taking a ketone and we are taking RMgBr as our Grignard reagent. Now this Mg is partially positive charge, you know, since it is a metal, it will have a positive charge. So this will interact with one of the lone pair of this oxygen. Again, now this R that we are having here, will again interact with another thing. So you will form a 6-member ring chain here. So what we are doing is we are taking one more mole of this RMgBr, and this again will form interaction with this, or you can say set up interaction with this carbonyl of this kind. So since this oxygen is having a negative charge, it will interact with Mg, and this carbon is having a positive charge, it will interact with R, and overall 2 molecules of RMgX we are having, like this. So first mole is this one, and the second mole is this one. Overall it makes a 6-member cyclic structure, which is very stable in nature. Now here we will get 2R from both of this RMgX. Okay, so both have 1 and finally we will get our product like this, which will be a alkoxide. At last we will do simply the hydrolysis to get our final product, which is this thing. So one reaction I want to mention here is that, so if you put H2O in this RMgR, it is very reactive. It will quickly give you your alkane, that is RH. Now next we will move to some oxidation reaction. So these are some important oxidation reactions. So we have studied earlier. So of the oxidation reaction, like our PCC, or you can say CrO3, Na2Cr2O7, KMnO4, and all those. So we will see more of them in the upcoming lecture. So when we will deal with our carboxylic acid. But today we will be seeing some mild oxidizing agent, which are also used as an indicator for the functional group. So suppose we have an aldehyde and we want to distinguish an aldehyde and a ketone. So we can do it using 2 tests. So we can have 2 tests. The first one is Tolvin's test, and the second one is Filling's test. So in Tolvin's test, what do we take? We take a complex of this Ag, coordination compound. It is a coordination compound. It is a complex of silver, which is having 2 ammonia, and it is having a linear structure. So we will take 2 moles of this, and in the presence of the alkaline medium, that is 3 moles of OH minus, we will get our carboxylate ion. Now upon termination of this reaction, or you can say detection of presence of this aldehyde, we will see a silver color, silver mirror. It is also called silver mirror test. So you will see a silver color. So this reaction is also called, or this test is also called silver mirror test. So plus we have 2 moles of water and 4 moles of ammonia. So this test is very important. So often it is asked in the exam that whether this compound or whether that compound will give Tolvins or not. Second, we have this Filling's test. So this is also for the detection of this aldehyde only. So both are for the detection of aldehyde. In this case, we take filling solution. So I will tell you later what is filling solution. So this filling solution mainly contains copper, ions and a complex which facilitate the reaction. So we will not get into this mechanism very much. And it is also happened in alkaline medium. Instead, only the moles is changed from 3 to 5. Again we get a carboxylate ion and it is detected by red brown PPT. So the first one is detected by silver color, second one is detected by red brown PPT, that is copper oxide, or you can say cuprous oxide, cupric oxide plus 3 moles of water. Now what is this filling solution? So this filling solution is mainly aqueous copper sulfate, which is CuSO4, which is an aqueous medium, and we have this alkaline sodium potassium tartrate. So tartrate look like this. We have one as a potassium and one as a sodium. So we have the sodium potassium tartrate. So one alkyl group is here. Okay, so this is a sodium potassium tartrate. So it is also called as Rochelle salt. So we take Rochelle salt and this copper sulfate solution to make our filling solution, which is filling solution A plus filling solution B. So this is the filling solution A and this is the filling solution B. So this is about the filling test and Tolvin's test. So both are used for aldehyde and it is done in alkaline medium. Okay, both give carboxylate ion plus silver is given in case of Tolvin's test, which is of silver color of course, and in filling test we get a copper cupric oxide which is of red brown color, which is a PPT. Now let us move to another test. So this test is also very important. It is called as haloform reaction. So what we do is we take sodium phosphide plus this haloform Na2PO3 plus this halogen, which is either Cl2, Br2 and I2. So F2 cannot be included. So F2 is not suitable for this haloform reaction. Now the reaction will proceed and it will give us again this salt of carboxylate ion, sodium carboxylate salt plus haloform. This is the haloform that we are having. And this carboxylate ion. Okay, so this was all about this haloform reaction. So you can take carbonyl which can have alkene group. So it is feasible with that also. Now next, what are the criteria for this haloform reaction to take place? So it should have this CH3CO group. So this is the most important criteria for this reaction to take place. So if you see in both of this reaction, you have this group here also. So this is the most important criteria for haloform reaction to take place. Now next, iodoform reaction. So if we use this iodine in place of for halogen, then you will get a pale yellow precipitate. So this will indicate that okay, nothing but at least CH3CO group is there in this compound. So this can be used as a detection test for also CH3CO. Now this reaction is not feasible with fluorine. So these are the important point for our haloform reaction. So let me make this thing clear again. So this group should be present. And if we take sodium phosphide plus I2, then it can be used as a detection test for this CH3CO, which will indicate by giving pale yellow precipitate. So fluorine is not good for this reaction. So this is all about the haloform reaction. Now we will move to the most important reaction of this lecture, which is aldol reaction. So this reaction is mainly due to the presence of alpha hydrogen. Now this reaction can happen in two ways. First is acid catalyzed aldol reaction and the second is base catalyzed aldol reaction. So what we do is we take a carbonyl compound which has a alpha hydrogen. So it should must have alpha hydrogen. So this is the most important point. So if we tell that only aldol reaction, then this is the product. So let me do it clear for you. Suppose we are taking a reaction, aldehyde, suppose that it looks like this. Now what we will do, we will take another mole. So it requires 2 mole of aldehyde. Now suppose this is acid catalyzed. Now what will happen? That's this CH3 which is looking like this. This is CH3 we have, and this is a lone pair. So this lone pair will take this thing. And we'll get this intermediate. Okay, so this is the first step that we are having. Now what will happen in the next step? So the another mole of CH3CO that we are having, it will attack like this at the carbonyl center. Means in this case, both of means both the character of reduction and oxidation, or you can say reducing or oxidizing agent, is done by the same molecule. Now it will form enol kind of thing, and in the next step we'll get sorry, this is wrong. Okay, so if you see it here, you can see that okay, the first is enolated. You can say it is taking this H plus, and we are getting an enol kind of thing. And the next step, we are doing the attack like this. Okay, so an enol is formed like this. Okay, so the enol, this is the formation of enol, so it will happen like this. So first this will be protonated, and it will move here, and we will get this thing here. Now this enol form is not stable, so it will quickly attack at this point. And we will get this kind of hydroxy ketone, which is beta hydroxy ketone, or you can say carbonyl for general case. So this is the thing that we got an aldol reaction product. So this is the aldol reaction. Now if you talk about aldol condensation, so it is a different thing. So we heat this in the thing, and a E1CB kind of reaction takes place. So what is E1CB? So it is elimination which is which is done with the help of conjugate base reaction. So what will happen? So this is an basic proton that we are having. So it will first move like this in the first step. So this happens only on heating. So this should be kept in mind. H. Now again this lone pair will move here and this OH will leave. So one mole of water molecule is being removed at this point. And what do we get? We get a alpha beta unsaturated carbonyl. So if you put this thing all over together, so what is aldol condensation? So aldol condensation is basically the reaction of two carbonyls which are out of which one will have this say alpha hydrogen in the presence of acid or base, and it will result in the formation of a alpha beta unsaturated carbonyl. So this is all about the aldol condensation. Now next thing is to thought about is that, so what is the regioselectivity of this aldol reaction? So if you want, we can take two different aldehyde or two different ketone, or you can say one aldehyde or one ketone. Then how will this reaction proceed? So if you look here in this thing, so we are having attack on this carbonyl center, and this is the RDS step here. So this attack, this RDS is attack. So attack is the RDS here. So we will not see the stability of this enol, rather we will see that which of this carbonyl center is more feasible to attack. So I mean, suppose we are having a ketone and we are having aldehyde. So if you want to form this compound, or you can want to see which one is major, of course 4 products will be formed. So if you name it A, if you name it B, so 4 products that are possible are, so 2 moles of A can do this, then 2 moles of BB can do this. A can attack on B and we can get AB, and B can attack on A and we can get BA. So if you see here, so which one is the major one? So we will decide this by which is having the most nucleophilic center. So out of this, you can see that this is the most nucleophilic center. So attack will happen on this. So B will attack on A. So this is the correct, you can say, or you can say the major one. Okay, so product is formed, all 4 are formed, but this is the major one. So how it will proceed? So first the enol will form, absolutely. Like this. So enol will look like this at last. I'm drawing the final one. And since this is a nucleophilic center, which is more nucleophilic than this carbonyl center because of the less steric hindrance, so this lone pair will move like this. And we'll attack here. Sorry. So this is the major one, and this are all the minor one. So you can try all the products by yourself. It will be a good practice for you. Now if you do the heating, of course E1CB will take place and you will get your product like this. So this was all about aldol condensation. So if you want, you can do it with the base also. So if you see here, so we form enol, but in base catalyzed reaction we get an enolate ion. So this is the enolate ion that we get, and now the reaction will take place with the help of enolate ion. So this is the difference between the acid catalyzed and the base catalyzed. So you can see very clearly, so we are getting an enol here, and for the base we are getting an enolate here. Okay, now this enolate will attack on this carbonyl center and we will get our final product. If you want, you can see it in the single step also. At last dehydrogenation takes place and we get our alpha beta unsaturated aldehyde. So if you want to consider the important point is that, so the important points are that that of course you can have two types of aldol reaction. So you can have cross aldol, in which two different reactions are taken, or you can have self aldol, in which same reactants are having 2 moles. Now it can be acid catalyzed and base catalyzed. Now if the case is the cross aldol, then one which is having less hindrance, or you can say more nucleophilic, it will be feasible to attack and will not form enol or enolate. That in case of acid we have enol, and in case of base we have this enolate. So this was all about the aldol reaction. So you must practice as much as possible. Okay, pushing arrows is a good practice for it, but for the exam point of view, you should have a shortcut. So I will show you it in the question. We will solve question. I will show you the shortcut method for doing for aldol reaction. Now next, what will happen if we do not have any alpha hydrogen? So for that case, we have another reaction, that is Cannizzaro. So Cannizzaro means no alpha hydrogen means what? So if you look what is alpha hydrogen, so let me make it more clear. Suppose this is the carbonyl center we are having, and this is the carbon that we are having here. So this position is called as alpha position. So this both are alpha. Now if there is a hydrogen here at this alpha position, then for that case we will have aldol reaction. And if not, no alpha hydrogen is present there, then in that case Cannizzaro reaction will take place. So this is the main criteria for deciding that whether aldol will take place or whether Cannizzaro will take place. Now what is Cannizzaro reaction? So it is a kind of reaction that happens in the absence of this alpha hydrogen, first point. Second point, it is a disproportion reaction. Why? Because the same thing, that is formaldehyde, is getting reduced. So it is getting reduced, and the same formaldehyde or another mole, means the next mole, is getting oxidized. So if you don't know how it is getting reduced, so the simple thing is that we are adding hydrogen to this carbon, so it is getting reduced, and we are adding one more oxygen to this carbon, so it is getting oxidized. So it is as simple as that. So what is formed in the reaction? A formate, or you can say a carboxylate ion, and the counter cation will be depending upon what kind of base we are taking. So it happens in the presence of concentrated base. Yeah, one more point, aldol happens in the presence of dilute acid or base, means the concentration is diluted. But for Cannizzaro, since it is a harsh reaction, you can see, because we are substituting it using OH, so we will take something which is concentrated. So we are taking concentrated potassium or concentrated sodium hydroxide. Now if you see here, this is the carbon, so there is no alpha position for this carbon. Similarly, this carbon has an alpha position, but it has no hydrogen present here, because one of the bond is of for the carbon, second bond is also carbon, and it is a pi bond again with carbon only. Now what is the product? I have told you earlier. So we'll get a carboxyl benzoate and we will get a alcohol. And one more thing, we will use 2 moles of this, say, because it is also like same, it is also same like this aldol, but we are not getting 2 products in case of aldol, but in case of Cannizzaro, 2 moles will react to give 1 mole of alcohol and plus 1 mole of this potassium formate or sodium benzoate, depending upon the substrate that we are taking. So this is all about the Cannizzaro reaction. Now we will see some reduction reaction. So we have earlier seen some of them, but this is a name reaction. The first one is Clemenson and the second one is Wolff-Kishner. So these two are important. You should remember the reagent first of all. So if you see here, so this step is nothing but nucleophilic addition, and of what? ammonia derivative. So how I'm saying that it is ammonia derivative? We have this NH2Z, and what is in the place of Z? NH2. So same thing is present. So it is a, for the first step is kind of, you can say, nucleophilic addition. So we will get an imine here. So we have seen it earlier. The formation of imine takes place upon addition of the ammonia derivative. And in the second case, second step, simply we take and reduce it using KOH and heat. And KOH in the presence of solvent, which is ethylene glycol. So this whole group is removed by 2 hydrogens. This is a kind of reduction reaction because we are adding 2 hydrogens. And this reaction is feasible due to the release of this N2, which is a very phenomenal leaving group. Now we can have again a reaction which will give the same product as the earlier reaction, only the side product will be different. So first Clemenson will give water and Wolff-Kirchner will give N2. But the substrate here we are taking is a zinc amalgam and HCl. So we will get our final product like this. Now let us see some questions to get our idea more clear. So I put this a kind of hybrid questions here, whatever we have learnt all about carbonyl till date. So what we are doing, we are taking P cresol. So those who don't know, this is called as P cresol. Next we react it with chloroform in alkaline medium to give the compound A. Chloroform means we are having CHX3. Chloroform is CHCl3. Okay. In the presence of alkaline medium to give the compound which A, which adds hydrogen cyanide to form compound B. So those who don't know, it is nothing but Riemer-Tiemer reaction. The first step is Riemer-Tiemer reaction. So Riemer-Tiemer reaction goes through this formation of carbene, which is not in your syllabus. I have not taught you here. Then in the next step, what will happen? Hydrogen cyanide will add. So in the next step is nothing but a nucleophilic substitution. So as we have seen what will happen upon addition of this nucleophilic. Now later on the acidic hydrolysis of this give chiral carboxylic acid. So we will do the acid hydrolysis of this cyanide. Now those who don't know, so this will come in the later on slides, later on chapters, that upon hydrolysis of this CN nitrile group, we get a carboxylic acid. So this is the final product that we have. Okay. So this is the product that we are having. So if you want, you can see the final product also. So this is the thing. So first is the Riemer-Tiemer reaction, which will give you this product. Then upon addition of HCl, we will get an intermediate. Then its hydrolysis give us this final product. So sorry for this case. So it will add on here. So correspondingly, you will get your carboxylic acid at the ortho position to this CH3. Now next, this is a consecutive reaction. So first what we are doing, we are oxidizing it. Okay, so we will oxidize it. So let us see the thing. So it will oxidize to give you carboxylic acid. So you can use here KMnO4. It is a strong oxidizing agent, and I have told you earlier, whatever be the alkyl chain with the benzene, if you take KMnO4, it will give you direct carboxylic acid. Then in the next step, we have a nucleophilic addition, which is SOCl2. So this OH is removed by Cl. Then again we have a nucleophilic attack by N3. So it will remove this Cl. So suppose this reaction is going in this way. We have this OH group. First, we have this SOCl2. So this SOCl2 attacks like this. So its mechanism is not as simple as the other nucleophilic attack. So this lone pair moves here. Okay, so this lone pair moves here and it's resonate back to give out this chlorine ion. Like this. Okay, now we have this chlorine. This chlorine will again attack here. This chlorine will again attack here and kind of create this one, Cl. Now this is a better leaving group, so it will resonate back and move this out to give us acyl chloride. That is will look like this. So this is the mechanism for from this step to this step. Then what we will do, we will take this N3. So this is the intermediate that we are having, Cl. Now this Na plus and N3 minus has this kind of structure. So it looks like this. Positive charge here, negative charge here, and negative charge here. So it will simply attack here. This will move up, it will resonate back and kick out this Cl. N plus and N minus. Okay. So if you want, you can do it like this and you can get this one. Now at last, N2 is a good leaving group. It is a very good leaving group. So it will just, what it will do, it will leave automatically and give you this kind of product. So it is a rearranged product. So if you want, you can do the arrow pushing by yourself. I'm not doing by here. Then next we have question number 3. So what we are doing, we are taking a alpha beta unsaturated aldehyde is formed in the sequence. So which one will give the alpha beta unsaturated aldehyde? So this will not give you. So which reaction gives us alpha beta unsaturated carbonyl? Aldol reaction. Now aldol reaction should have alpha hydrogen. So this is the first criteria. So if you see here, it will not give the aldol reaction because it has no alpha hydrogen. Second, this is alpha hydrogen. Okay, so this will have alpha hydrogen. It can give this say our required product. Now you can eliminate both of this at one time only. So because this is not a carbonyl, first of all, so it will be eliminated by itself. Now this one will not give you alpha beta unsaturated. It will it will give you beta hydroxy ketone because heating is not involved here. So only the one reaction that is to be predicted to give this alpha beta unsaturated is CH3CHO. So this is the reaction. Next, which of the following is the product of aldol reaction? So this is a kind of reverse reaction you have to follow and say which will give you the final answer. So here is a trick for this. So if you want this one to reaction to take place, so you will see where the bond that is forming here. So which one is the aldol product first of all? So aldol product is basically beta hydroxy ketone. So this one is not a beta hydroxy ketone because this is the beta position and OH is present on the gamma position. Similarly, it is present at the alpha position, so this is also eliminated. At last, we can have this one as your alpha beta hydrogen, beta hydroxy. So let us see it what is the which of the following the product, it can be a product of aldol reaction or not. So if we break this bond, and if we break this bond, let me do it for you. So what is the possible reactant that we can have? So this must be the carbon that has attacked on this carbon. This is the possible reactant that we can have for this. Plus this will also. So it can give our aldol reaction. But if you look at this one, which is a B, which has a structure like this. If you break this one, so it is already having 3 bonds. Okay, so it cannot form O, carbonyl O here. So it is not possible for this to give your required product. So this is the place they attack, sorry. Yeah, so this is the correct answer. Okay. Now next question number 5. Iodoform can be prepared from all except. So which can give iodoform? So this is ethyl methyl ketone. Ethyl methyl ketone. So it will look like this. So it has CH3CO. So it will give you the reaction. Isopropyl alcohol. So isopropyl alcohol looks like this. Methane, ethane, propane. Then 2-methyl. So it does not have CH3CO group, but let us see other reactions first of all. 3-methyl 2-butane. 3-methyl 2-butane non. So it will look like this. So it does not have a CH3 group. This is CH2. This is H2. Yeah, this is having a 3-methyl. Okay. So this is also having a kind of CH3CO group. Now this is a very important question. Why? Because it is an exceptional one. You will say that okay, both are alcohol, both will not give you required product. But we will see that one as a possible iodoform reaction giving one, which can form your ketone. So if you look at this one, which is isopropyl alcohol, so this is a very important case. You should remember this. We can make carbonyl from this. So we can make carbonyl from this without breaking any carbon-carbon bond. So we are not required to do so in this case. So this is just a trick to remember. So I'm not giving you the details here. But if you want a carbonyl to exist, you must have to break any of these 3 bonds to make carbonyl out of this. So second thing, it is a CH3 group, of course. It is a CH3 group. This is also a CH3CO group, but it is having a breaking of carbon between these 2 carbon. So due to this reason, this one will give haloform. So alcohols also give haloform. So you have to what should you remember? So if you form the alcohol to carbonyl at that point only where alcohol is attached, and after forming that ketone or aldehyde, you do not need to break any CH3 CC bond first, and after the formation of carbonyl, it should have a CH3CO kind of group. Then in that case, you can have this haloform reaction. Same thing written here also, that okay, this will not give a required product. It's not prepared from your third butyl. So now I will give you some questions. So it is a very famous questions. I'm not giving you the options here. Okay, so for this question, so you will see one by one all those questions and try to solve it by yourself. So this was all for today. We will see our next chapter today, which is carboxylic acid, tomorrow. Okay, thank you for your time.